Hello again. The last third of this unit is on solubility equilibrium. So far when we've talked about equilibrium, we've talked about it in terms of solutions, aqueous solutions. We've talked about it in terms of reactions that exist as gases. And this is kind of a subset of those solutions. This is, solubility means literally when something dissolves. So this is going to be the equilibrium that is established, when you take a scoop of any ionic compound, barium sulfate, sodium chloride, any of them, and stir it in water. And that's the equilibrium that we're going to be looking at today. There's a couple of the topics that deal directly with this. This is saying that the dissolution, that means dissolving, right? The dissolving of salt is a reversible process. When we have this is from like last year. When we have a saturated solution, we know that the solution is dissolving at the same rate that the aqueous particles are recrystallizing, and that those two processes are happening at the same rate. That's what equilibrium is all about. It can be affected by pH. And this last one, 17.14, is actually one that we are not going to do until we talk about entropy. So those solubility rules that you looked at last year, it was always soluble or insoluble, like one or the other. And what, we know in AP Chem is that sometimes what we learned sophomore year needs a little bit more refinement. And that's exactly what this is all about. When we said that those compounds were insoluble, it didn't really mean that none of that compound dissolved. What it meant is that very little of that compound dissolved. And now we get to actually put a number to it. So what is very little? What is a lot? We do that by looking at something called the solubility product constant, or KSP. SP stands for solubility product. It's the same rules as always. Products of reactants, coefficients become exponents. And the key thing here is that we get to leave out the solid and the liquid, and there will be, in a dissolving process, there will always be a solid. So here is a typical balanced chemical equation for an ionic compound dissolving, and the KSP would of course be just as we would have predicted last chapter, the concentration of barium 2+ times the concentration of sulfate over nothing, because the reactant is a solid. So this is going to be kind of interesting because none of these are going to really have denominators. So write the expression for the solubility product constant of calcium fluoride and then look up the value. So calcium fluoride, right, as a solid, when it dissolves, it will of course produce the calcium 2+ ion, and this is key that we get these coefficients correct, 2F-, right, because it's CaF2. So the KSP for this is the concentration of the Ca2+ times the concentration of the F- squared. And we will have way more exponents, we will have exponents in these a whole bunch of times. The numerical value for this KSP, you can look that up in Appendix D, was 3.9 times 10 to the negative 11. That's a very small number. So what that means is that for every, think of 3.9 times 10 to the negative 11, or 3.9 times 10 to 11 of these guys, one of them will actually dissociate in water. So very rarely does this dissociate in water. And what we are going to learn to do is to go from KSPs, which we can look up, to molar solubility, which is a much more typical unit to describe how soluble a substance is. And basically we're going to do that through algebra, that once I have the KSP, I can then figure out with x's and solving for x, the molar concentration of the ions, and then using the empirical formula, thinking about, well, the number of fluoride, think of this guy, that, if I know the F- concentration, I can use the fact that 2F- came from 1 mole of the actual ionic compound, and then go back and get either molar solubility or regular solubility, which we usually do in terms of grams. And I can also, make this process go the other way as well. So this first problem is going from molarity to KSP, going from molar solubility to KSP. So solid silver chromate
Remember, silver is always a 1+ ion, so we don't often actually need to put the numerical value, we don't need to actually have the Roman numeral in there, but it is always +1. Silver chromate is added to pure water at 25 degrees Celsius. Some solid remains undissolved. This is how we know it's at equilibrium. It's a saturated solution. The mixture is stirred for several days to ensure that the equilibrium is established. Silver chromate and the solution. Analysis of the equilibrated solution shows that its silver ion concentration is 3.1 times 10 to the -4. Assuming that this is saturated and it's the only equilibrium, calculate the KSP. So the first thing I like to do is write out a balanced chemical equation. So it'll be Ag2CrO4 solid in equilibrium with 2Ag plus aqueous and CrO4 2 minus. And then think about we will eventually get to a place where we'll sort of maybe skip over this process, but let's look at an ice chart here, right? The initial, first of all, I'm never going to worry about that entire side because it's a solid. The initial, right? Initially, these guys would have 0. And this is very important. I know that at equilibrium, the silver ion concentration is 1.3 times 10 to the -4 molarity. Which means this guy must have gone up by 1.3 times 10 to the -4 molarity. What does that mean for the other ion, for the chromate? Well, look at the coefficients, right? I will get twice the silver ion for every 1 chromate. So what did this go up by? Well, half that, right? So 6.5 times 10 to the -5 for a total of 6.5 times 10 to the -5, right? So I'm using the coefficients in order to figure out what that final row is going to be. And now I could just put it right into my KSP, right? KSP is the concentration of the Ag plus squared times the concentration of CrO4 2 minus. The Ag is 1.3 times 10 to the -4 squared. The chromate is 6.5 times 10 to the -5, and that comes out to be 1.1 times 10 to the -12. Again, these K's, so they don't have units on them. Okay, here's a very similar type problem. Feel free to pause here and try this one on your own. If not, we'll do it all together. A saturated solution of magnesium hydroxide, pH is found to be 10.7. That's going to be key because I know that if the pH is equal to 10.17, then the pOH must be equal to 3.83, which means the concentration of the OH minus is 10 to the -3.83. If you need to go back and refresh your memory on all of those pH, pOH concentration, go back and refresh your memory on that because it will become important in this chapter and the next unit. So here is the balanced chemical equation, right? These guys both started at 0, but I know that at equilibrium, I know that the OH minus concentration is 10 to the -3.83. And then I can plug that in my calculator, get an actual answer. I believe it comes out to be 1.47 times 10 to the -4, which means that the magnesium must have also gone up. But again, look at the coefficients here. It must have gone up by half as much. So magnesium must have gone up by 7.395 times 10 to the -5 for 7.395 times 10 to the -5. KSP equals the concentration of the magnesium times the concentration of the OH minus squared. So 7.395 times 10 to the -5 times 1.47 times 10 to the -4 squared, or 1.62 times 10 to the -12. And then the other type of problem is just literally going backwards, going the other way, KSP to solubility. So here's the KSP for calcium fluoride, and it's asking us calculate the solubility in grams per liter. Again, I always start with writing a balanced chemical equation, and then, looking at, would an ice chart help me out here? And usually it does. I don't know. These guys are going to start at a 0. This is going to go up by x. This guy is going to go up by 2x. So x and 2x. And now I go and I can plug it into my KSP. KSP equals the concentration of the Ca2 plus times the concentration of F minus squared. I know the KSP is 3.9 times 10 to the negative 11. The Ca2 plus is X. The F minus is 2X, and that's all squared. And students will often think this isn't right. I'm taking that into account twice, the fact that there's twice as much fluoride. But it is right. This is exactly how you do it. So now we just solve using algebra. 3.9 times 10 to the negative 11 equals, and when you do that out, it will equal 4x cubed. That's going to actually happen a lot, that the right-hand side is going to equal 4x cubed. When we solve for x, we get x is equal to 2.13 times 10 to the negative 4. That is going to have a unit because it is going to be a molarity. And then I need to think about, well, what does that equal? That equals, right, the concentration of the Ca2 plus. And because the Ca2 plus has the same coefficient as the CaF2, I know that if that's the number of moles of Ca2 plus in solution, that must have been the number of moles of calcium fluoride that actually dissolved. So therefore, I know that the molar solubility of CaF2 is equal to that number, 2.13 times 10 to the negative 4 moles per liter. Then the question goes on to ask us for it in grams per liter. Okay, so I actually didn't do that calculation beforehand. But of course, you would simply find the molar mass of calcium fluoride and then multiply the molar solubility by the molar mass to convert moles into liters. So in units grams per liter, because that's what the question is asking us to find, is 0.01 grams per liter. We have a couple more of these sort of practice problems for you. Of the 5 salts listed, which has the highest concentration of its cation in water? Assume that, all salts, this is the only thing going on. So what you need to do for this one is basically just what we did for the last one. Think about lead 2 chromate, PbCrO4. That would be, what would be the solubility product constant, Pb2 plus CrO4 2 minus. Or basically this would be x times x, or x squared. So if x squared is equal to 2.8 times 10 to the negative 13, then x, right, would be the cation, would be 5.3 times 10 to the negative 7. And I would do that for all of the other ions themselves. Okay, so if you look at what I did, I basically figured out what would be the concentration of those cations. I didn't even do them for these two, because just in my head, looking at 5 times 10 to the negative 22, taking the square root of that, I know it's going to be something times 10 to the negative 11. It's going to be much smaller than the ones that I already have. And so of the ones that I did, 6.87 times 10 to the negative 6 is the largest, and that is for the cobalt 2 hydroxide. And then the final question, this is another one where here's the KSP, and the question is asking what's the solubility in water, right? So we write a balanced chemical equation for this. This will be, they start out with 0. If this guy goes up by x, this guy will go up by 3x. And then the KSP, which is 2 times 10 to the negative 19, equals x times 3x cubed, which is, what the heck does that equal? 27x to the 4th, and that means x is equal to, and that would of course be the concentration of the concentration of the La, lanthanum, 3+, would be 9.28 times 10 to the negative 6. And because the lanthanum ion has the same concentration as the lanthanum fluoride, this can also be thought of as the molar solubility of LaF3, would be 9.28 times 10 to the negative 6 molarity.